Okay, this is the last thing that we'll be doing in Chapter 11, and this is called the Ideal Gas Law. And what this law does is combine all the variables that we've been exploring. And so we played around with the relationship between pressure and volume, and we know that this is an inverse relationship. This little squiggle means that this is proportional, doesn't mean equal to. But the increase in pressure results in a decrease in volume and so on and so forth. We also know that we've played around with volume and temperature. And we know that volume and temperature are directly proportional, so we'll write that like this, meaning that as the temperature increases, the volume increases. And finally, we played around with the relationship between pressure and temperature. And we know that pressure and temperature are also directly proportional, meaning as you increase one, you increase the other. And the last one that we looked at, Avogadro's law, says that volume is directly proportional to the number of moles. So what we're going to do is we're going to take these four variables and we're going to plug them into an equation. Now, if you remember in all the, well, we'll worry about that later on. Never mind. Forget what I was about to say. So here's how this is going to work. We're going to take these four variables and we're going to put them into one big equation called the ideal gas law. And it looks like this. PV equals NRT. So we actually pronounce this PIV NERT because it makes it easier to remember. And let's make sure we're cool with all the variables. This is pressure. And we're going to use the unit atmospheres for this one. This V, this is volume, and we're going to record volume in liters. This N, this is moles, and it's just how many moles we have. So that's the unit. And this guy, T, this is going to be temperature, and we are going to make sure we put this into kelvins. So what's this guy, R? And so R is pretty special. R is what we're going to call the ideal gas constant. And it's nice because it puts everything else into a nice tidy relationship. And it works like this. R has a specific value. It is a constant, meaning that the value for R never changes. As far as we are concerned, this value, whenever we see the letter R in chapter 11, this will change later on, but whenever we see the letter R, it's going to have this value, 0.0821, and it's going to have a very strange set of units. The units are going to look like this: liter, atmospheres, or moles Kelvin. And I'll explain why these units look so weird. So let's take an example of how we're going to use this equation. And you're going to want to be able to flip this around. What I mean is, if you know that PV is equal to nRT, you're going to want to be able to find each of these variables. So if you're trying to find P, you would divide both sides by V, and that would look like this. If you're trying to find V, you would divide both sides by P, and that would look like this. If you're trying to find T, you would divide both sides by NR, and that would look like this. And if you were trying to find N, you would divide both sides by RT, and that would look like this. So up to you to be able to flip these around. Sometimes I'll show you, most times I won't, but you'll get the hang of it. Let's take this for a quick spin and I'll show you what I mean. Oops. So here's the kind of question you could expect me to ask. And notice it says, what volume are we talking about? That means we're looking for V. So what I like to do when I'm doing one of these is I like to say, okay, we know that piv nert is our original version of the equation, and if we're trying to find V, that means we're going to divide both sides by P. And because I like to establish what my variables are, we know that N is 12 moles. It says it right here. We know that R is a constant, 0.0821 liter atmospheres over moles Kelvin. We know that T is our temperature, 25 degrees Celsius, but we want it in kelvins, so we'll call that 298 kelvins. And we know that P is our pressure, 1.4 atmospheres. It says it right there. So let's plug all this stuff into this equation and see what we get. It's asking for volume. We know N, 12 moles. R is a constant, 0.0821 liter atmospheres over moles Kelvin. Temperature is 298 kelvins. We're going to divide all this by P, which is 1.4 atmospheres. Now, why does this unit look so weird? Here's why. Atmospheres cancels atmospheres, moles cancels moles, kelvins cancels kelvins, and leaves us with liters, which is what we wanted. We wanted to find volume in liters. So all we need to do is take our calculator. Let me turn mine on. And I'm going to do all of this in one shot. So I'm going to use the parenthetical function on my calculator. So I'm going to put 12 moles times 0.0821 liter atmospheres over moles kelvins times 298. I'll close those parentheses and I'll divide this whole thing by 1.4. And this will give you my answer in liters. 209.7, and we'll record that right here. All right, so I'm going to need you to practice flipping this stuff around and finding this variable or that variable, but you'll get the hang of it. Okay, I'll talk to you later.